Good afternoon and welcome. We recently got hold of a Dektak stylus profiler, and Edmond's going to give us a review. He's been working on it. He has some examples, and so this should be exciting for users as an overview, and then he'll give a live demonstration. Dr. Chow has been with us for quite a few years. He is a senior research engineer, and he's an excellent person. If you have any questions about our metrology tools or e-beam lithography.
All right, thank you, Mark. So today I'm going to show you how to use our new Dektak stylus profiler to measure surface roughness and film stress. And at the end, I will do a live demo in using it to measure the step height measurement. So let's just cut to the trace to talk about surface roughness. So as most of you already know, typically we characterize the surface roughness by using the root mean square value. So shown here is a profile. C is the height, and the scan in the X direction, we scan 4 millimeter. And you can see each data point represented by the black dot here. So root mean square value, just to remind you, we first find the mean or the average. So the C bar is the average. In this case, we shift it such that the average is at 0. And then the root mean square value is just subtract each data point from the mean, take the square, sum all the data point, and then divide by the number of data points and take the square root. So this is pretty straightforward, root mean square value to characterize the surface roughness. But in reality, when we actually use the stylus profiler to measure the profile, that's typically what we get. So shown here is a profile measured on a glass substrate. Again, the scan length is 4 millimeter. And you can see that the profile height difference is about 275 nanometer. But most of this height change is due to the tilt of the stage. And you can imagine even with a very small tilt, 4 millimeter with a 0.005 degree already has 270 nanometer. So the first thing after we measure the profile is we have to remove the tilt. And we simply subtract the slope by drawing a line from the beginning to the end. And we change this original raw data total profile that is called in the software. By removing the tilt, we will create the so-called primary profile. So this profile, the primary profile is simply subtract that slope due to the tilt. But after we get this primary profile, we still cannot directly apply the root mean square value equation to get the roughness. Why is that? And the reason is when we talk about roughness, typically we are referring to a short range high variation. In this case, the profile actually also convoluted with the wafer bowing, and it has about 40 nanometer. So if we directly apply the root mean square value equation, all we get is this wafer bow, okay? However, in most cases, we are interested in the short range high variation. So the way to extract the roughness, short range high variation, is we apply a long pass filter. The long pass filter we set here is about 1/10 of the scan length. So 4 millimeter, I set it at 0.4 millimeter. This is kind of rule of the thumb, but it also depends on what kind of roughness length scale that you are interested to set that long pass filter cutoff. But by doing that, you can see that with the long pass filter, any high variation that has a length scale longer than 0.4 millimeter, it gets passed on to the red curve. That is what call as a waviness profile in the software that will allow you to measure the wafer deformation. But whatever it reject by the long pass filter is shown in the blue curve, and that's what we call as a roughness profile. And that's where we generally apply the root mean square equation to extract the surface roughness, RMS value. So now that I show you all this long pass filter and how to extract the roughness profile, let's apply it to the silicon. So shown here is a roughness measurement on a bare silicon 4-inch wafer. And again, the black curve is the primary profile after we move the till. And the red curve is the waviness profile. And the blue curve is the roughness profile. You can, if we focus on the blue curve, the roughness profile, you can see the peak to peak is about 1 nanometer. And if you apply the root mean square equation, what we generally do is we actually choose the middle section. So too close to the end of the scan or the beginning of the scan, the data may not be reliable. So when I do the measurement for the rest of my talk, when we do the 4 millimeter scan, when we analyze the RMS value, I focus on between 1 to 3 millimeter, the center portion. And we apply that equation, we get the RMS about 0.5 nanometer. Just to show you a zoom in how the data looks like, let me just, so I want to zoom into this region from 1 millimeter scan to 1.5. The scan was done with a 2 micron radius stylus, and the status sampling rate is about 1 data point per 0.015 micron. And you can see that in one peak here, this peak here corresponds to this peak, and this peak here corresponds to this one. The reason I want to zoom it in is I want to make sure the peak we see is not just a single pixel, that the noise from the measurement system. You can see there are more than 10 data points for those peaks. That is because we actually have pretty high data sampling rate. And despite of that, the scan speed is still pretty high. The total scan for a 4 millimeter scan is only about 12 seconds. And because of that high scan speed, it allows us to check some statistics. So we could repeat the measurement on the same wafer for a certain number of scans, and to look at the statistic and see how the RMS value change from scan to scan. So shown here is again measurement on roughness measurement on a bare silicon wafer. We actually measure on 2 different wafers, and we repeat the scan 50 times with the same scan length, 4 millimeter, use the same long pass filter cutoff. You can see that the RMS value within one wafer or even across 2 different wafers is about 0.5 nanometer. And the standard deviation from scan to scan is about 10%. And in fact, the way that we repeat the scan is not to, I didn't scan exactly the same position. What I did is I scanned 4 millimeter. I move up 100 micron because the stage is fully automated, fully motorized. So I moved 100 micron up and scan again. I repeat 50 times. And again, use the same data sampling rate. This time though, because of the stage movement, each scan takes 12 seconds, but when we move 12 seconds to move it back to this point, it takes a similar amount of time. So to repeat one scan, we actually need 23 seconds. To do it 50 times, it takes about 20 minutes. But because we do it the scan, repeat the scan every 100 micron in the Y direction. So this axis here, in addition to represent the number, measurement number, it actually also represent the Y direction. So basically, at each Y position, we have one RMS value. And what I try to see is to see how uniform it is as we move in the Y direction. And it looks pretty uniform, at least about 10% of the standard deviation. So now that we established certain confidence that the RMS value is quite repeatable, the absolute value may not be exact. I mean, due to our stylus radius is 2 micron, but within the same system, we can certainly have some confidence in use it to compare the roughness with different process. So the first process I try to compare with this bare silicon is to compare with a PECVD silicon nitride deposition. So after I measure that silicon wafer, I put down 124 nanometer silicon nitride and repeat the same 4 millimeter scan. May not be exactly the same position, but since we checked that, it actually quite uniform across the wafer, at least within 4 by 5 millimeter. On the top is the scan done after the silicon nitride deposition. On the bottom, I just show you the old data, the profile, the roughness profile. Here's, that's where we focus on. We use the long pass filter to extract the roughness profile. And you can see that, again, for the bare silicon, the peak to peak is about 1 nanometer. However, after 124 nanometer PECVD nitride, you can see that the peak to peak is about 2.5 to 2.5 nanometer. So let's look at what the RMS value after the silicon nitride deposition. So again, the red data point, we repeat 50 times using the same fraction that we move every 100 micron, every scan, we then move 100 micron in the Y direction. And again, this axis kind of represent a Y-axis, the Y direction of the wafer. And you can clearly see that for the silicon, bare silicon, we have about 0.5 nanometer RMS, plus minus 10%. For the silicon nitride deposition wafer, after we deposit 124 nanometer silicon nitride, you can see that the RMS are basically double. Again, the standard deviation at different Y position is about 10%. So this showed that the stylus performometer, despite that the radius of curvature is 2 micron, fairly big, it actually can distinguish the surface roughness before and after the nitride deposition. Now, after I see that, I want to see how about etching. After doing the deposition, how about I etch the silicon and see the roughness? How does it change? Shown here, again, I repeat the measurement after the silicon etch about 2 minutes, okay? We repeat it 50 times. Again, in the same fashion, I move 100 micron every scan. But this time, the standard deviation is way bigger. You can see that for most of the scan, I guess for half of them, the RMS is still about 0.5 nanometer, not bad. But we see all those spike. And it ends up, if we do the standard deviation, you can see that that is huge. The average RMS is about 1.1 nanometer, but then there's a huge variation as we move along the right direction. So to understand what happened, I'm going to look at 3 different scans, scan number 5, scan number 10, and scan number 42, and look at it to see what happened. So you can see the green one, scan number 5, the roughness is pretty small. You basically cannot see it on this scale. However, for scan number 10, you see a huge peak. For scan number 42, you actually see 4 peak. However, the RMS only focus on from 1 to 3 millimeters. So basically, this RMS only represent the data that with 2 peaks. And that's why you can see that the RMS here is about 4 nanometer and here is about 2 nanometer. Now, because of this highly non-uniform RMS, as we move in the Y direction, what I try to do is, how about we do a finer scan? This one is scanned every 100 micron. Let's do a finer scan. So we can, before that, sorry. Before that, again, I want to show you that each peak has correspond to multiple data point, and it's not just a noise. So now let's look at a finer 3D scan. I call it 3D scan because normally it's a 2D line scan. This time, I did an 800 scan, each one again 4 millimeter. But instead of scan for every 100 micron, this time I choose every 5 micron. And the reason is our stylus radius is 2 microns. So scan anything finer probably won't give you any higher resolution. And even we do an 800 scan, it takes about 5 hours. So I just set it up the night before and start the scan. And that's the next day I got this data. Okay, so I cover a 4 by 4 millimeter. Obviously, the X direction scan is more higher resolution. The status sampling is higher. The Y direction is 5 micron, right? So after the 3D scan, I do see a lot of spike, a lot of particle. And to understand that, I look at the SEM. So when I look at the SEM, on this etched silicon wafer. So this is a low mat SEM picture. This corresponds to 100 micron, 0.1 millimeter. I indeed see some low density defect, okay? And when I zoom into this particular defect, I find that the defect is about 4 to 5 micron long, about 100 to 200 nanometer tall, and actually only about 200 nanometer wide, or 200 or 300 nanometer wide. I was quite surprised it still get picked up. I guess it's because of the length of the defect is fairly long. It still get picked up by our stylus profiler. So because of that, it can pick up those defects. Then I thought maybe we can do some defect density estimation in terms of the density. So the software allow you to set some threshold in the height, and basically it allow you to say, okay, anything that is taller than 100 nanometer, I will call it as a defect. And with this 4 by 4 millimeter scan area, it will count for you to see how many defect with the threshold that you set by the software. So in this case, I set it to 50 nanometer. I got 38 of the defect. And you actually also allow you to sort them. So basically, it sort the highest point. Number 23 here correspond to this guy. It actually close to 2 microns. So that's probably not what I see in the SEM picture, that kind of defect. So you allow the software automatically allow you to, you can ask it to calculate different parameters like the area of the defect, how big they are, and also sort them, the diameter and so on. But even though we know that the stylus profiler cannot detect a 2 micron radius, cannot detect a very small defect, but that if we consistently use the same threshold, use the same scan, we can potentially compare how the defect density change between different processes using the same recipe for measurement and analysis. It can also mask out those large defects and give you a background roughness as well. And I have to, I want to mention that this software will be available for any user in HMNTL to download it into your office. So you can save your analysis recipe. So make sure you use the same long pass cutoff and all the detail. And then you can repeat analysis the same way for different processes. And that way will allow you to compare the roughness, compare maybe your defect density and so on. So with that, I'm going to switch gear to the next topic, which is mechanical stress in dielectric film. Shown here is a cartoon. So the blue region represents a dielectric thin film, and the gray region represents the substrate. Mechanical stress has two different kinds of stress. One is the compressive stress. In the compressive stress case, the film wants to expand. You can see the outer diameter, the film is on the outside, the outer diameter is bigger. They try to expand, but confined to the substrate. And therefore, it will create a convex band. And as you remember from your calculus class, convex band means negative curvature. And that's why compressive stress has a negative sign associated with it. Another kind of stress is tensile stress. In that case, the film wants to shrink, but it's confined to the substrate, and therefore it creates a concave band. And this corresponds to a positive curvature, and therefore tensile stress is also associated with a positive sign. In general, for fabrication, we would like to reduce the film stress so that we minimize the wafer bowing or distortion, so that we avoid the delamination, cracking, and avoid lithography problem. You can imagine if you have a very thick film and a significant stress, that will create a large enough wafer distortion that the depth of focus of your lithography system may be smaller than the distortion and create problem. So in general, most cases, we want to reduce the film stress. However, we have many different research groups at HMNTL also take advantage of the film stress. For example, Professor Suling Lee's group has well known to create this roll-up silicon nitride tube using high frequency and low frequency PECVD nitride. By engineering the stress, they can control how the tube get rolled up on a release structure and create an inductor. Another example is Professor Kiji Fang's group. They use aluminum nitride to create a photonic circuit, and they use this kind of nano coupling coupler for coupling light between fiber. And again, they have to make sure they use the right film stress when they release the material. They want their coupler to tilt a certain way, a certain angle. So the point here is whether you want to reduce the film stress or you want to take advantage of the film stress is an important parameter to be able to measure in the process. So how do we do it? In film stress, there's a well-known Stoney equation where the sigma film stress can be characterized by this equation here. So the stylus profiler will measure these two parameters, R post and R pre. They are the radius of curvature. Pre means before deposition, post means after deposition. Those are the parameter which use the stylus profiler to measure. And then we will use the substrate parameter represented by the blue symbol. The substrate material has a Young modulus and the Poisson ratio and the substrate thickness. So we have to input those parameters in order to get the stress. It also depends obviously from the film thickness, TF. In the software, they provide a material library for a couple common substrate material with the Young modulus and allow you to, if those are the material that you have for the substrate, they will automatically calculate the stress for you after you measure the radius of curvature. If you have a material that is not in here, you can also enter those parameters and get the stress. So now that we know how to get the stress from the radius of curvature, the next question is, how do we measure the radius of curvature with the stylus profiler? And I use here an example of a 4-inch wafer, 100 millimeter wafer. Our system can measure film stress from 2-inch wafer all the way up to 6-inch wafer. One way to do the film stress measurement, at least the way that I find it useful, is we first make a light scratch near the center of the major flat. And then we also use the major flat to align the orientation so that the major flat is parallel to the x-axis of the stage. And the reason we do that is it's very important to measure the radius of curvature along the same path before and after the deposition. So this is just to mark the location, mark the direction of the scan using the major flat and the scratch. So after we make a light scratch, typically about 2 millimeter long, we will move from the major flat edge up 10 millimeter. We don't want to scan it too close to the edge because there may be some edge effect, right? Same way, and then we will scan 80 millimeter for a 100 millimeter wafer. We don't want to scan all the way to 100 millimeter, again, due to the edge effect. So after we make that scan, this is the profile. So this is the profile, the C profile. We scan from 10 millimeter all the way to 90 millimeter. This is a profile before deposition. And then we create a, we use the raw data, the black one, and then we create a 5-degree polynomial fit. And the reason we do that is because it allows us to do analytically derivative. If you remember from your calculus class, the radius of curvature is defined this way, both the first derivative and the second derivative. After we get the polynomial fit, then it's very easy to calculate those derivatives. And therefore, we can get the radius of curvature at each data point. And after that, then we are ready to get our film stress by plugging to the Stoney equation. Shown here is the blue curve is after deposition. So I plot 1/6, 1/r post times those substrate parameter and the film parameter. So because I multiply by those quantity, so the unit is basically the same unit as the film stress, named in this case I use gigapascal. So I do the same thing for the radius of curvature before deposition. And after that, I will analyze the data from 8 millimeter to 72 millimeter. Again, I don't want to use the data to calculate the L-phase stress from near the edge. So I cut 10% off. Since I scan 80 millimeter, I start from 8 millimeter and measure the stress to 72. And that's what I get. So I got to get the stress, we simply subtract the blue curve from the green curve. And you can see that the blue curve is always higher than the green curve. That means we have a positive stress, the tensile stress. And we only focus on the data from 8 millimeter to 72 millimeter. So basically we have about 0.37 gigapascal all the way to about 0.6 Pascal. And then we take the alphage, and the alphage we got is about 0.465 gigapascal. And this is tensile stress, it's positive. So now that we know how to measure the film stress, I'm going to show the data that provided by Patrick Su, Professor John Dallesasse's group. In this case, he is trying to do a film stress control with a dual frequency pulse process. If you remember 3 weeks ago, one of the Oxford process engineer, Greg, he also explained the same kind of film stress control using dual frequency pulse control. So basically, for high frequency, most PECVD use 13.56 megahertz. You will create tensile stress. If we add a low frequency RF, typically less than 1 megahertz, in our case, it's 360 kilohertz, that will create compressive stress. In his talk, I asked him why is that, and he explained that at low frequency there will be a significantly more ion bombardment, and because of the ion bombardment, the deposition, the atom can actually squeeze in a smaller volume, and therefore it will expand. And for the detail, you can read about it in this theoretical paper. But for now, I'm going to show Patrick's data. So his experiment is to change the high frequency pulse fraction. So I plot here the stress as a high frequency pulse fraction. What do I mean? What I mean is for 0 high frequency pulse fraction, it means 100% low frequency. So there's no high frequency component. So the entire deposition was done with 380 kilohertz. And for high frequency pulse fraction at 1, it means it's all high frequency. So all the deposition was done with 13.56 megahertz. At 0.5 pulse fraction, it means that with 10-second high frequency, followed by 10-second low frequency, and then repeat. So the cycle is 20 seconds. For the rest of the data point, basically, he keep the 20-second cycle, but then the exact ratio of high frequency and low frequency component defined by the high frequency pulse fraction display here. And you can see that as expected, the compressive stress show up that for the for lower high frequency fraction, basically for the frequency fraction less than 0.75, he see mostly compressive stress as expected. When we go to higher frequency, we see the positive stress, the tensile stress, and again, as expected. And you can see there's a cluster of data point here that is we scan multiple times, and that's a typical variation. We can't actually exactly scan the same path, but it's still fairly small, about 5%. And we also compare the data that we got on the same wafer. So again, I plot the film stress as a function of high frequency pulse fraction. But this time the data was measured by our film stress measurement system that is based on laser-based curvature scanning. For the most part, they agree fairly well, except maybe 1 or 2 data point here. probably because we didn't have a motorized stage here. It's much harder to repeat the same position for the scan. So after that, I also want to show you within one wafer, how repeatable is the film stress measurement by using the Dektak stylus profiler. So I plot here the film stress as a basically measurement number. I basically measure it from May 5th to June 22nd for about 25 times. And you can see that it's fairly consistent. With the average is 196 megapascal and with about 5% standard deviation. With that, I will summarize. I basically show you that by using a long pass filter, we can separate the wafer waviness correspond to the long range height variation from the short range surface roughness. And for uniform surface, a 2D scan may be sufficient for RMS roughness measurement. If you have a non-uniform surface like what we described in the etching silicon etch surface, you might need to do a more detailed 3D scan, and that can also potentially allow you to estimate the defect density. Finally, I show you the film stress measurement as well as Patrick's dual frequency pulse stress control data. And with that, I'm going to do a live demo. So let me stop share this screen and let me share another screen from. Okay, so I hope you can see what I'm showing here. So I'm going to show you how to do step height measurement with a fully automated motorized stage. So I'm showing here the sample. The first thing I usually do is to, you can see it's kind of tilted. I'm going to show you how to rotate it so that it line up parallel to the stage. So very easy, just make horizontal and you choose the first reference point, move there, click OK, and then you move to another point that is supposed to be in the same axis. So I double click here. So this is supposed to be the same Y coordinate. So I click OK, and then you will rotate to the where you want. The next step is I'm going to show you a fully automated measurement. So in this, this green rectangle basically represent this rectangle here. I'm going to ask it to align to this point and then align to this point, and then I will ask it to move up minus 250 micron and start scan. So this way will allow you to scan the same position every time, at least within the stage movement precision. So I'm going to start the recipe. I'm going to click here, automated measurement. And then it will move to where it thinks the corner should be. So it cannot move exactly the same position because I cannot place the sample exactly the same way, but I'm going to help it. So I'm going to say, okay, this point here actually corresponds to here. So I double click here. If I can't click it very well, I can zoom in, just double click it, looks okay. Then I will click next, then you will find this point. And if it line up well, then I will just click go ahead measurement. If I'm if I think it's a little bit off, I can help it to find a better position. So now I think it's pretty good. Then I will click finish. Once it's finished, then it will go to the designated point to start scan. It's going to do 3 scans. So it will do first scan, And I have to point out that there's a bug in the software that during the display, this number is actually not quite right. But after the data, after they finish the scan, it actually display the correct number. So now it moved to the second point, basically in the middle. It moved about 200 micron and do another scan. So it will move to the next point here. All those points are designed by the user, and then you can save it in your automated recipe. And that way, if you have some calibration test point in your sample, you can choose to go to exact the same point and using that to allow you to get better statistics. So after I finish the measurement now, then I will click OK. And then you will actually do an automatic etch detection and actually plot out the step height for you. So basically, I repeat 30 times on those steps, and you can see this is in angstrom. So basically, I measure the same thing. The average is only different by less than 25 angstrom, less than 2.5 nanometer, repeating 30 times, peak to peaks. So it automatically save for you. You can create a database. You will get all the information. You can also export that data to your favorite software to do more analysis. So I think I will stop here to answer some. If you have any question, then we can answer that. So.
So if you have any questions, please feel free to type them in to the chat screen. So the first question is, how do you choose the data sampling rate?
Data sampling rate, basically, as long as it's high, I mean, obviously, you want the data sampling rate to be able to take advantage of the stylus radius that you have. Since there's not too much overhead, oversampling is not a problem. And when we oversampling the data sampling rate, we can actually use a low short pass filter. So you can imagine that if you use a 2 micron stylus, any height variation that is shorter than 2 micron is probably not real. So we can oversample it, but then we will use a short pass filter to reject those high frequency noise, and that's I usually oversample it, and then to make sure we are not getting the noise, I use a short pass filter to reject those high frequency component that is not supposed to see with a 2 micron stylus. They also have to mention that the stylus that Dektak provide, the smallest one is 0.2 micron. We didn't purchase that because it's fairly fragile, and for a shared facility may not be very feasible. However, individual group, if you like to purchase your own, changing the stylus is actually fairly easy, very easy to do. So there are some other laboratory that individual group actually purchase their own stylus, especially for the very fine one. And we can change it for you for your measurement and do it that way.
What is the source of the small periodic variations in the silicon wafer profile?
Let me see. I don't quite know what you are referring to. I mean, again, I guess I don't know. I don't know what is the source of the surface roughness for for the silicon surface.
So is that your expectation that that is the smoothness of the silicon itself?
I believe that the silicon should be smoother, and the fact that we get 0.5 seems to be a little bit higher than I expect. I probably expect 0.1 or 0.2 nanometer RMS. But my thinking is, since we can at least distinguish between the nitride deposition and the silicon deposition without deposition, it is still a useful information, and by no means that it will present a true RMS value of the wafer. I will say in that case is a upper bound, and if we use the same equipment to measure, for such a smooth surface, we probably cannot get an absolute RMS value, but we can compare before and after the process, and that's how I would use it for such a smooth surface like bare silicon.
We already had an alpha step line scanner. Why bother buying the Dektak? What will it do that's different than the old alpha step? And why is it worth using?
Well, I'm sure you will find it much easier to use, but one of the main reasons that we decided to purchase that is for a reliable film stress measurement, and that was one reason we actually choose a kind of the high-end model is the fully motorized stage, and with the fully motorized stage, it allows you to go to the same spot much more reliable than a manual stage. And you just cannot do the film stress measurement with our old alpha step. This one, I mean, yeah, you can't scan a 4-inch wafer, and you cannot go to the same spot easily. And so I guess on top of a 3D, the alpha step also cannot do a 3D scan. And but I guess the main reason that we choose this system is to be able to get us a film stress measurement that is reliable.
When you did the live demonstration, it looks like there's some kind of mechanics of 2 points coming in together. If it's a single stylus, do you know what the 2 points are coming in from the side?
The 2 point, one of them is the refraction. So the top, I mean, the left one is the actual stylus, and the right one is just the refraction. So when you come into contact, you see 2 of them touch.
Can you measure the profile of small cleaved pieces instead of whole wafers?
Definitely, you can measure small pieces. The only thing that is potentially a problem is you can't use the vacuum to hold a small piece, but in most cases, it's stable enough that you can just put it on the stage and let it scan. Yes, so you can scan very small piece down to a few millimeter.
So since this is stylus based, that means the stylus is touching the wafer. Is that right?
Yes.
Have you seen any artifacts indicating that it leaves any kind of residue, alteration, or damage to your sample?
Okay, with that, I'm going to show one of the slides that from MRL webinar. So in that case, I think Kathy and Julio give a very nice presentation on the 3D optical performance. And yes, I mean, compared to the force, the AFM is nano-Newton. And in our case, is 10 millinewton. So yes, the force is stronger, I mean higher. And if you want no contact, I guess 3D optical performance is one good way to go.
In your use, have you seen anything left over so that the
No,
sample measurements change as you do them?
I have not seen anything left, and it's fairly easy to clean the stylus. And the way that we are told to clean the stylus is we put a 4-inch wafer on the stage, we put a clean room wipe, we spray some IP on the clean room wipe, and we ask the stylus to engage to the clean room wipe that is on top of the silicon wafer, and that clean the stylus very well. And we don't need to use a Q-tip or anything to touch it. We just ask it to land it on the clean room wipe, and the clean room wipe have IPA, and it cleaned it very well.
Very good. Thank you very much, everyone, for attending. I don't see any new questions, so I think that will be a wrap.
Thank you.